Good. So, calculating pi. Okay. So, does anyone know how we can calculate pi just in general? Like if someone came up to you on the street and was like quick, okay, like, you know, how do you write an equation that solves for pi? You know. So, yeah? Exactly, yeah. So there's like weird kind of like pure math summations that exist that will calculate pi for us. And I'll just quickly show you. So there's actually this great Wikipedia page that is all about the modern quest for more digits of pi. And it talks about different ways to calculate pi. And this is kind of the most classic formula to calculate pi. And so what we could probably do is we could write some C++ program that just runs this like a bunch of times for a bunch of different iterations. You can see here, so as we increase n, it gets closer and closer to pi. So if I increase it to 100, you can see it's 3.15. If I increase it to 1,000, you can see it's 3.142. So it's like off by still a little bit. And as we increase the number of iterations, then we get closer and closer to this value of pi. You can imagine probably C++ could be probably really good at this, running like just a for loop and doing all these like complex math instructions really quickly. So this is the Gregory Leibniz series from around the 14th or 15th century. And the issue with it is it's really slow. Like, look, it took 10,000 iterations to be able to get like 5 digits. So this is not actually what's used nowadays for people who try to break world records for calculating more and more digits of pi. Instead, there are a bunch of different methods, but a common way that people used to use more was this Ramanujan series. So this, I won't even begin to explain to you how they figured out all of these like random numbers and things, but you can see what's going on. Actually, why is it? Hopefully, maybe, oh, there we go. Okay, so if I just shrink this down a little bit, if I shrink it to like 10, you can see that even with just one single iteration, we're already really close to pi. It's 3.14159265359. Actually, that might already be like good. So if we go and we take, if we like take the value of pi and like find the difference of these two, you can see it's like a very small number. Like these are almost exactly the same. And as we increase the number of iterations, you can see actually immediately Desmos can't even calculate like the difference between the two. So this is a much better implementation potentially for, if we wanted to implement this in C++. Okay. How would we maybe write a program to now calculate maybe, the first like 10,000 digits of pi now using this? So what I would do like immediately is I'd probably just put it into ChatGPT, because a lot of this kind of just looks like kind of boilerplate like stuff. So by the way, anyone use Desmos? Okay, good, yeah. Desmos, fantastic. Do you know what happens when you copy like a Desmos, like if you select and copy something from Desmos and paste it somewhere else? Do you know what it copies as? Okay, let me paste it. Okay, does this look familiar? So this is just straight LaTeX right here. So that's super helpful. ChatGPT, really good at handling LaTeX. So what we can do is probably just take in, like, we can select this and then feed it into ChatGPT, and it'll probably be able to help us out quite a bit. So that is like my first thought. So I could be like, note that Desmos, right? So it's taking this this is a summation, and we are doing a bunch of different iterations, right, up until n. But maybe we should just have a single function that just runs for one single iteration. Maybe we could just pass in this value of k right here. So we pass in value of k, and it gives us that one single term. So that's kind of my first thought. So what we can basically just do is take this and then ask ChatGPT. We can say like hello, I have this expression in terms of k. We could say implement it in C++ as a function with input k. And it's going to be like really good. Actually, okay, I'm gonna undo this because I don't like when it does that. what I like to do is I like to turn on this reasoning thing right here. I'm going to use reason. It's pretty good. It's just like pauses for a second. Yeah. Sure. So now we can run this. Is there a question? Oh. It is available for free users. Yeah, I've never paid for this. Yeah. Other question? I don't know why it's taking a second. I don't know why it's taking so long. Well, what the heck? Uh-oh. I guess so. Okay, there we go. So it's reasoning, so it'll take a second. But then it'll spit out for us all of the code. We could have probably implemented this ourselves, but it's just nice to have it already kind of done for us. Sure, so now we can go and copy this, and we can make a source directory, right? And probably, I don't know, just do like main.cpp, good, copy, done, awesome. Well, maybe now what we could do next is, oh, there's another bird in here. Well, maybe now we can go and take this whole thing, and we can go and replace it to now where this term, maybe we say that this is like f of k. Now we can go and paste this in to ChatGPT. We can say, like, great, can you now implement this function? And this function, this should be in terms of what? So it's no longer going to be in terms of k. What is this going to be in terms of? Yeah, this will be probably in terms of n, like the number of iterations. So, okay, good. So can you now implement this function? Note that f is a function. Okay. And yeah, it's, this is fine. Okay. Cool. Is this how people use ChatGPT? Good. Fantastic. Okay. And this is kind of cool. So actually, it looks like it recognized that this compute term function was actually the same in both cases. So it actually automatically kind of filled that out for us. So that's great. So now we can take this, and it's probably already really good. Now we can go and compile this, src, g++, main.cpp. Oops, that's okay. We can look at the main that was generated. It looks like it says enter n, and then we give it an n. So we can maybe give it I don't know, 100 or something. Okay, well, maybe we can give it something smaller, maybe 10. Okay, there we go. That's pretty good. Actually, that looks really good. Okay, let's see now. Maybe, okay, so here it's setting the precision to 20 decimal points. Maybe if we want, we can print out maybe 100 decimal points. Okay, so I'll say, go for 10. So there we go. Okay, let's increase this. Let's say maybe go for 30. Okay, good. So does it look like the value changed? So when we ran it for 10 iterations, it doesn't look like much changed compared to when we ran it for 30 iterations. Okay, sure. So maybe that means that we are successful. Maybe that means that it, it is correctly computed the same, the correct number. Let's go and now run it for a precision of maybe 1,000 decimal places. Let's see if it's computed it for that. So if I ran it for 30, what's going on? What? Okay, you know what? That's okay. I don't know. It was working differently. Well, what I'll tell you though, I was going to visually show it, but for some reason it's not working now. Is there an issue with this current implementation? There's probably a few issues, but there's a big one right here that I was trying to demonstrate. And what is the issue? Yeah. Yeah, well, that's a big thing. You're right. So we are returning this double right here, but a double is can only store, what is it, like 20 decimal places. So when we try setting the precision to like 100, it's actually not going to be able to compute to like 100 decimal places properly. Okay, so this is an issue. This is actually a big issue if you ever want to do anything in any sort of math field that requires extremely high precision in numbers. Fortunately, the GNU team created an open source library for dealing with arbitrary length floating point numbers. Has anyone heard of this before? Okay. So this, yeah, this is a totally like reasonable thing. Like you may be like, actually, I don't want to use floats because yeah, floats like the max that's only like 32 bits. I don't want to use doubles because that's only 64 bits. Instead, I want to be able to just pass in any width. Like I want like a float that's effectively like 1,000 bits long or something. And you can do that. And what I would probably do then is just go and pass this back into ChatGPT and be like, hey, like, thanks. Can you now implement this using the GNU implementation for arbitrary length floats? Cool. So it'll take a second to figure it out. Take a second, taking a second, taking a second. That's like one kind of small issue with doing live demonstrations with the ChatGPTs. It's not always the fastest. Okay. Okay, there we go. Cool. So it's working. Oh, so okay. So it looks like it recognized. So it's GMP. I believe GMP stands for. Actually, we can look it up in the meantime. So GMP Wikipedia. Right, good. No, what is it? Oh, yeah, the GNU multi. It is actually installed. I did that before this lecture, so I installed this. Yeah. So okay. Remember, so when you write like a CMake file and you do find package, you have to do two things. So the first thing is setting your like probably include path, which I already have done like behind the scenes. But what is the other thing that you need to do? It starts with an L. Okay. What is it? Linking, yeah, exactly. So we need to link it. And we specifically need to link it as a third-party library. So what I would do is I would go and just basically just copy and paste this, put it back into ChatGPT. But maybe I'd say like, hey, it looks like it's not linking properly. And I can remove the reasoning to like speed it up a bit. I can say, how do I compile this to properly link the shared library? Okay. What's the difference between shared libraries and static libraries? Shared libraries versus static libraries. Yes? Exactly, yeah. So a shared library is a object file that is outside of your binary. So when you ever want to like distribute your binary, you are not giving people like your full program. Instead, you can have, a shared library, meaning it's a library that exists somewhere else. So then they could have that shared library like pre-installed on their computer. And then when they go and download your library, it's like a smaller file. Yeah, so that's the idea with shared libraries. So yeah, in this case, we want to use a shared library. So I guess I should have hit enter before I went on that spiel. But there we go. Okay, looks like it properly gave us the link commands now. So I can do and/main. Okay, compiling. Notice that it'll take a little bit longer. What's going on? Why did that not work? I don't know. Okay, it's fine. So, okay, cool. So in theory, it now is working. So we can run it for, it's like 10 iterations. Okay, 3.14159. Can we change the, here, let's go and ask it, can you print it? Where was that? Yes, that is fine. I was looking for just a way to print it as like more digits. Can you print it to 100 decimal places? Okay. All right, cool. Okay, whatever. Sure. So in your opinion, though, so if you notice, though, it was running quite slow, even just for like 100. Yeah, if we run it for 100, you can see, okay, that was actually pretty quick. If we run it for 1,000, that's actually also pretty quick. If I run it for 10,000, that's pretty slow. Yeah, actually, that's really slow. Okay. If anyone were to guess, what would probably be maybe the slowest thing in this? Why is it taking so long to run it for 10,000 iterations? Okay. You should be like kind of screaming at yourself. There's a very common kind of like example in here that's like one of the like memoization 101. Yeah? Okay, wait. Yes? Sure. Okay, yeah, so we have all these for loops, right? Okay. This is computing integer power, I guess. Sure. And but then also, yeah, we have this one that when we pass in this like n, it will run this for loop. Sure. Okay. We have this one as well. Okay. In any of these, is there one that kind of like looks the most able to be optimized? Yeah? Yeah, I think this factorial function, we can probably really optimize this. In fact, I think we're probably going to be spending like a long time in this factorial function if we were to like put it into a profiler. Or we could actually double check that. We could actually put it into a profiler to check. So, okay, now imagine this was a final exam question that was, here you are given this executable, go and profile it. What function takes the longest amount of time? That's a totally reasonable question. So let's go and test this. So what I can now do, if I want, I can say, hey, can you show me how to profile this with Valgrind? Because I don't remember the commands off the top of my head, which I probably should. But I think it's like Valgrind. Yeah, tool call grind. There we go. So now we can go and test this out. So I'll go and run valgrind on this, and we'll run it for maybe just 1,000 iterations. That'll probably be pretty good. Notice how much longer it's taking. Before, when I ran 1,000, it finished in like 1 second. Now it's finishing in like maybe like 5 seconds. Why did it take so much longer on this time? Why does valgrind slow down, or why does profiling code slow down execution? Okay, what was that? Sure, the snapshot, yeah. It's because what happens, the profiler will halt execution every maybe like, I don't know, 100 microseconds or something. It'll pause the execution, and yeah, it'll take a snapshot of the call stack, and then it will resume execution. So it's like pausing and then unpausing, pausing, unpausing. And that will slow down execution. So there we go. So now we have just ran Valgrind. And let's see, did it give us I don't remember oh yeah, there we go, cool. So this is how we run, this is how we open the GUI. So let's go and check this out. So I believe, there we go. Okay, so open this up. We'll see exactly like how long it's spending in each one of the functions. It's taking a second. Go. Okay, cool, okay. Factorial. Can we see how long? Kind of small, but can you just see how long factorial ends up taking here? Yeah, it looks like it's spending like 40%, 44% of its entire execution time just running this factorial function. So this is potentially a good opportunity for us to optimize this. We can also see, actually, it's spending a long time in iPower as well. So maybe we should also optimize this. Let's start with factorial, though. This might be a better place to start. Okay, yeah, how do we optimize this? Roughly. Okay, turn to the person next to you. If you were in what's the algorithms class or the data structures class? 102? Okay, imagine, final exam question on 102. It's like, oh, make this factorial function run faster. What is the answer? Tell the person next to you. What was that? Sure. Factorial just being called right here. It's passed in an integer in compute term, and then it's also being called here. Okay. What do we do? What do we do? Someone else? Yeah? Today's the last day for you to participate in lecture. Just throwing that out there. Anyone? How do we make this run faster? Okay. Yes. Absolutely, yeah. So we can have a cache. We can have like a memoization cache. We can just store any time that we've computed that output before. That is extremely useful in factorial, because if you need to calculate like 50 factorial, it's like, that's going to take a while. But if you now want to calculate, if you right after that want to calculate 51 factorial, well, what you should probably do is just grab what you just calculated and then multiply that by 51. And that should be like super, super fast. So yeah, what we can do is we can just put on some sort of cache onto this. And the common kind of way of doing this is maybe you have like an unordered map, and you just take whatever the function, or you take whatever the input is, and you make that your key to your hash table, and then you make the value whatever the return value is, and you have some like check right here that's like if the hash table already has that member, then go and just return that member. If it does not have that, then calculate it like normal, and then go and store that into the table. So that is generally how factorial is implemented, is you have this big memoization thing. Okay, what is potentially an issue if I now wanted to calculate like 10 million factorial? I take it back. What if you want to run like 1,000 factorial? What is potentially an issue with this? By just having by storing every single function call in this array, what is potentially an issue? Okay. Someone else? What is an issue? Yeah. Exactly, yeah, the size of the cache. We potentially could be storing huge data, especially if, we're storing this this multi-precision class object, because these objects, these are very big, right? They're storing arbitrary length integers or whatnot. So yeah, they're storing potentially huge bits of data. Okay, what's a potential solution to this then? Because remember, as we move like further and further along, as we compute bigger and bigger digits of pi, right, what happens to our inputs that we are passing into factorial? Yeah? That's the point of using the arbitrary length data value. So in theory, it will never overflow. Yeah. So I guess what I'm getting at is as you keep going on and on and on and on, you are going to actually have your the input to your factorial function will always increase, meaning you are always going to want to grab bigger and bigger factorial values. That is useful because now you could probably throw away a lot of old factorial values that you don't care about because you're never going to have just like completely random factorial values. So you don't need to store every single value. Instead, you could probably just store like, yeah, maybe you could store only like the 100 most recent factorial values that you care about. And then when you occasionally fill that up, like once you've gone past 100 factorial elements, maybe you go and pop out whatever the least recently used object is. This is totally reasonable. Yeah. If you've taken computer architecture, hopefully you've probably heard of like a least recently used associative cache. You could do the exact same thing in this. Yeah. Okay. We could spend a couple minutes writing it out, or we could just ask ChatGPT. So let's go and do that. Okay. Turn to the person next to you though, and in your opinion, how should we input this into ChatGPT? What are what do we do? What is the prompt? And is there anything specific that we should do? Like, should we click on any extra buttons and things? Like, what is the best way to get the best answer out of ChatGPT at this point? Okay, go and tell the person next to you. Tell them what you would do if you were handed this computer. It's like, oh, this is my next step. I'm going to quickly mention, so I accidentally deleted this file ahead of time. There's actually this cool website right here that has a text file. It's like a gigabyte, and it has 1 billion digits of pi right here. So I'm actually going to grab it, and we're going to use it to verify our answer in a little bit. So I'm just going to grab it. If you now wanted to download this, I copied the link to it. What could we do to download this from the command line? Does anyone remember the command? Yes? Yeah, so we can use curl. There's another one. What's the other one? Yeah? Sure. I'm just saying, I just want to download this file from, this random page. My favorite is just wget, because you don't need to add any extra command line arguments as opposed to, curl. You have to put in a couple more. So I'll do this. It'll take a few minutes to download because it's big gigabyte file. But okay, cool. So let's see. Hopefully ChatGPT is. That's right. Hopefully you've all come up with a good way to prompt ChatGPT now. What do? How do we get it to produce a memoized implementation of factorial? Okay. Yes. Yes. I passed in specifically this link to this .txt file. It will download whatever is at the link that you pass in. However, you can actually ask it to grab an entire website, and you can ask it to grab things recursively. But just by default, without any other arguments, you can just specify the link. Yeah. So yeah, here, if we wanted to click on this link and see what's inside of it, we would see that this is the massive gigabyte file right here, and it has all of the numbers and stuff. Yeah. Cool. Okay. How do we get factorial out? ChatGPT. Okay. Yes. That's true. Okay, yeah. So we could do that. We could make a memoization wrapper that could just be put on like any C++ function. We could do that. I think that it might be a little bit overkill at this moment, and I don't have that prepared right now. I will say that like I've attempted this in the past, and it's not trivial to do that. One of the reasons you also would need to pass in like a hash function into the template itself, so it gets kind of complicated. Instead, I would just recommend doing it just specifically for factorial in this case. Yeah, another idea? Yeah. Sure, okay. Yeah, we could ask ChatGPT, we could just ask it if it has experience in specific memoization techniques. What I can kind of just thinking is like, I'm just trying to get to the like minimum viable product like as soon as possible, I guess. Like if I just wanted to give me some sort of code. Yeah. What I'll tell you right now, so yeah, what we could probably do is just say like, could you now re-implement factorial using memoization. Note that this factorial function, it uses this for loop here, but to use memoization most effectively, generally, you want to use not a for loop, but you want to use something called what? It starts with an R. Yeah, recursion, thank you. So we probably want it to use recursion instead. Please use recursion instead. We could also have it not use recursion too, but I don't think use recursion. Yeah, question? Sure, so we can make it do the L or U stuff. I think maybe for now, let's just say, we can tell it like, don't worry about L or U for now. But yeah, we could ask it for that as well. There is another issue that I have with the way that we are currently prompting it though, and that is that ChatGPT actually has a really bad memory, especially on this like free model that I'm using, because I don't pay for it. But what happens, like if you look at like how much text it just spat out, like it has to keep all of this in its memory. And if I scroll up, like it's having to think through all of this, all of this, all of this. This is all Valgrind stuff. I don't need to care about this. And then it also needs to keep in account my prompt, and then it also needs to look at all of this as well. So what I would do instead is go back to probably like an earlier time. Like actually, I could even go back here. Like it doesn't need to keep track of like every single token in this big error message that I'm sending it. So I can just keep scrolling up. Actually, it looks like it looks like this is probably a good place to start. So I would put right here. I would go and put my prompt in right here instead. I'm editing my prompt at this point. I'm editing it so it keeps less of its memory full. This is an extremely useful technique. In this case, it's maybe not as useful because there's not, like these prompts are not huge. Actually, this is quite large. But what you will find, like if you're doing, like if you wanted to pass in like a huge PDF of something, like some big API standard or like a bunch of code, then you like really, it really pains you to like try to have ChatGPT like hold several things in its head all at once. So therefore, yeah, I'm always in the habit of scrolling up and like deleting an earlier post. Yeah, look, we've like just made it so that it's going to forget all this now. So okay, I'll hit send. And I'll enable reasoning now. So hopefully this will give a good answer. Cool. In theory, maybe this will get us closer to the output. I will also quickly pull this other function that I grabbed, and we will just kind of use this. I'll pass this into ChatGPT as well. Okay. So, cool. Okay, looks like it. How does this look? Does that look roughly correct? Any issues with that? Look good? I think it's okay. Okay, so now we can just copy this, paste it in. Okay, let's go and run this. Let's close out of Valgrind. Okay, let's run it for 1,000. So that was, felt pretty quick. Okay, let's do, I don't know, 10,000 maybe? I guess it's actually still running for a little bit. Well, you know, in theory it should be faster. We can run it now in Valgrind and see. Hopefully it is faster. So if I run it for 1,000 now. I guess I didn't actually measure it, but okay. It's annoying. 3.6. Okay, so I just reopened Valgrind, so now we can check. Okay, does it look like factorial is running for less time now? Yeah, actually it looks like it sped it up quite a bit. If we look down here, now it's only running for about like 1% of the time. Okay, so we were successful. Cool. Let's quickly verify, though, that we are, in fact, running this for like all the correct digits. You can see I've now downloaded this pi billion txt file. So yeah, it's like a gigabyte file with all different digits of pi, at least the first billion. And I have this function right here. Where is it? This function right here. It's called verify pi, and it just verifies the correct number of digits. So I'll just pass this into ChatGPT now. And I think it's fine. I don't think we need to go back and edit this prompt. I think it's okay to now continue. So I'll say, like, I have this function. Okay. What? Okay, go and tell the person next to you, quick 20-second discussion. What is my next bit of prompt that I put in? While I go charge my computer. Okay, what's next? Need someone else? What do we type in here? Anyone? Should I just hit enter? Are we good? Okay, yeah. Yeah. Oh, my point with this is I want it to use verify pi now to verify that that at least ChatGPT's code that it wrote for me is correct. So that is the purpose of this. So how could I write this prompt now to have it now spit out code that uses this? That is my goal. Okay, yeah. Uh-huh. Okay. Could we use it to check the code that we wrote? Maybe another thing, so I can tell it about that we already have this file, and the file is called pibillion.txt. I have pibillion.txt that is, what should I say? Yeah? Perfect. Yeah, contains the correct output. I'll say first 1 billion digits of pi. Okay. Cool. So let's do its thing. Is this similar or different at all to how we already use ChatGPT? Like, is this kind of what people already do? Because I've looked on, people will come to me in office hours and they'll be like, oh, I'm trying to use ChatGPT, and I feel like I don't always see people using it in the most efficient way. Is this at all interesting? It's like, oh wait, I've never thought of prompting ChatGPT in this way or something. Okay, somewhat useful. Oh no. Yeah, definitely. I mean, yeah, being like verbose with your prompts. Looks like it broke again. So let me just refresh this. Did it work? Okay. Okay. Oh, yes, question. Yeah, it doesn't. Right. It doesn't. Yeah, you can still see them. So if I scroll up back to this, I can actually see, I can like click over and I can click and be like, oh, show me my previous prompt, and I can see my previous like tree of information. But, oh no, why can't I get back? Oh no, what's going on here? Oh, there we go, okay. But what's nice is when it does its token generation, it won't factor in any like previous messages that you've sent. And this will help it like make the correct answer, because that way it's not like having to keep too much in its head. Yeah. Just like trial and error. Like I find that it works way better if you give it longer prompts that are correct the first time. Like basically, like you'll see on my ChatGPT conversations, I'll have cases where I'll give it like 10 prompts all in a row, but it'll be just me editing the same thing like over and over until finally it gives the correct thing. Because I find like if I say like, oh, now change this, now change this, now change this, now change this, it's going to completely forget what I originally said at the very beginning. Yeah. So, okay, cool. So working now, so is it using verify? Yeah, it looks like it's using verify pi, so hopefully it's going to work now. Actually, it looks weird. Why is it? Oh, I see. Okay. It's fine. All right, I'm closing out of these. So hopefully this is going to work. Could not open file. Oh, that's right. /source main. Okay, cool. Bad starting at 77, so we've calculated 77 digits of pi correctly. What if we do 1,000? Oh, it still says 77. That's not good. Okay, what if we do 10,000? So okay, it looks like it's still getting caught on 7,000. Do we see anywhere that could be an issue? Oh, you know what? Is this? Is that an issue? I don't know. You know, it went in a slightly different direction. Oh, this is interesting. Well, you know, I'm not exactly certain, but there's more that we could probably do to do this correctly. Last time it like kind of worked immediately, and it got me to like 8,000 digits pretty quick. But yeah, you can continue playing around with it. Yeah. What about this? Okay, sure. Yeah, anyways, okay. So the last like couple things though. So if we were to just keep going with this, like maybe our next thing would be like maybe it was working for like 8,000 digits, but then the question would be like maybe you would be given this code on the final exam. It's like, okay, you are given code that calculates 8,000 digits every second, or like 10,000 digits every second. Now the new question is, how do you make it run faster? Okay, if it were you, what is something that we could potentially do to speed this up? So if you remember, right, so what this is basically just doing is calculating a term, and then it's adding it to the final result. And it's calculating the next term, adding it to the final result. And it's doing this for like 10,000 iterations. So is there some way that we can speed that up? Anyone do homework 7 yet? Yeah, multi-threading. Yeah, okay. How could we potentially multi-thread this? Yeah? Absolutely, yeah. So we can break up this compute final value, and maybe we could have like some sort of num threads input attached to this. Yeah, and maybe we say compute term runs from, like maybe k to n divided by num threads. And then the next thread will run from like k, whatever, n divided by k threads to 2 times n divided by k threads or whatever. And then you could go and chunk it all out. Yeah, and you could absolutely do that. What else would you need to do if that was your implementation? Probably, yeah? Sure, yeah, and then you just combine it all back together. If you wanted to, you could still use just this like single series sum thing. You could maybe put like a mutex lock around this. Yeah, okay. Is there going to be another issue? Like, are we maybe going to have a race condition for factorial? I think potentially we might. Yeah, absolutely. So we actually might want to put a lock around this static memo thing right here. Maybe we want to make a static lock or a lock that only exists in this in this scope. Yeah, absolutely. Okay. Another thing though is if we are making the first thread work for maybe like the first 1,000 iterations, second thread work for the next 1,000, third thread work for the next 1,000. If we now think about what each thread is doing individually, like in this factorial function, like how it's calling the factorial function, does that mean that each thread will actually be doing the same amount of work, or will some threads actually be like given an easier problem to solve? Yeah. Exactly, yeah. So if you are putting in like the 10,000th term, it's probably going to take a while to calculate that 10,000th term. Probably needs to calculate like, 30,000 factorial or something. That's going to take a non-zero amount of time. Versus, if you have like one thread that like it just is calculating the first 1,000 factorial, it's probably going to run really fast. So maybe another strategy you could think is like, well, how do I make it so that each thread is roughly doing about the same amount of work? That could also potentially improve your efficiency. So, okay, any final questions on this? Any final thoughts? Any final ways that we could potentially speed this up? There's actually probably a couple dozen ways that we could speed this up even more. There's like caching stuff we could do. There's like very complicated like more math operation, arithmetic stuff that we could do to speed this up. We could probably implement our own like faster version of this like multi-precision library to speed it up. So I guess it's also just like how much time you have. Unfortunately, the ChatGPT answers was not as good as last time. I guess I can quickly show you what it was able to do when I was doing this example earlier. What's going on? CD. I can just do source dot old main. Sure. So if I did like 10,000, I guess it still takes a while, but maybe I'll just do 1,000. Okay, there we go. You know what? It's not shown. I think I was on an old version. Anyways, it's accurate to like 8,000 digits, so I'm happy with that. Okay, cool. So that is everything. So potentially everything that I talked about today could be like used in like a kind of reasonable final exam question. So if you have any questions on anything, please let me know on Piazza. The last couple minutes of class, I'll just head out. I'll stand outside. If anyone wants to just take the last few minutes to do their sets right now, they're welcome to. I'll hang out outside for another like maybe 5-10 minutes in case anyone has any questions. So yeah, thank you very much, everyone. You are excused. Fantastic job on everything this quarter. And okay, I'm gonna go outside. So I will, please take the time to do the sets if you can right now.